Yeah, hello everyone, and thank you for joining. Today we have Wei Xing, and she will talk about Frieze patterns and cluster categories. So thank you very much for your time, Wei, and uh, please start when you are ready. I hope I pronounce your name correctly. Please correct me if I'm wrong. So thank
Okay.
you very much for your time, and please start when you are ready.
Okay. Thank you for the invitation, and thank you everybody for attending to this talk. So today I would like to uh, talk about some connections between Frieze patterns, which are very much combinatorial, and cluster categories, which is arising in a homological algebra way. So, sorry. So we divide the talk into three parts. So firstly, we introduced the Conway-Coxeter Frieze patterns, which was firstly introduced by Coxeter and later on studied by Conway and Coxeter together. Um, and then I will move to cluster algebras, and we will restrict to the cluster algebras arising from quivers. And of course, I will explain how they are related to Frieze patterns. And eventually, I will introduce the concept of cluster categories to explain certain phenomena that show up in Frieze patterns. And the main content in this talk is based on lecture note by Matthew Pressland. It's called From Frieze Patterns to Cluster Categories. You may find it from arXiv. Okay, let's start. Conway-Coxeter Frieze pattern is a strip of positive integers, as you can see from this example. The first and the last rules consist of only ones. And all the other ones are given by positive integers, and moreover, they satisfy the so-called diamond rule, which means whenever we have a configuration of A, B, C, D, which form a diamond, they should satisfy the equation that AD minus BC equals 1. So, and we call the number of rows with non-trivial entries the height of the Frieze pattern. So in this example, the height of this one is 6, because we can see that we have 1, 2, 3, 4, 5, 6 non-trivial rows. So a priori, if you just randomly put integers.
Excuse me.
Sorry.
Sorry to interrupt you.
Yeah.
Professor Sohail Khan is requesting because they are not able to hear us.
Okay. Okay. No problem. So maybe let's just continue with the definition of a Frieze pattern. So a Frieze pattern consists of a strip of positive integers such that the first row and the last row only consists of ones. And moreover, whenever we have a diamond configuration, then the four integers A, B, C, D, as you can see from here, they should satisfy the equation that AD minus BC equals 1. So this is called the diamond rule. So a priori, if you just randomly put positive integers, there's no guarantee that you will go back to the ones. Conway and Coxeter studied these patterns and tried to give a classification. Because of the diamond rule, we can see that if the second row is fixed, then by applying the diamond rule, we can get all the other entries. So in that sense, the second row, because of that, the second row of this strip is called the quiddity sequence of the Frieze. And again, if we just put a random sequence here, we cannot be sure that while applying the diamond rule, we would be able to get positive integers always. So there are certain restrictions on such sequences that when they can be a quantity sequence of a Frieze. And the simple observation from this example is that we can see some periodicity of this sequence. That if you go like 3, 1, 2, 3, 2, 2, 2, 1, 5, and then we come back to 3, 1 again. And this is in general holds true for Frieze patterns. And indeed, Conway and Coxeter give a very nice bijection between such sequences, which can be quiddity sequence of Friezes, and triangulation of polygons. So let's recall the triangulation of a polygon. So we fix a polygon on a plane. And the triangulation is a maximum collection of pairwise and non-crossing diagonals. So in that sense, this polygon is divided into a bunch of triangles. That's why it's called a triangulation. And if we associate to each vertex integer to record the number of triangles that are instanced with this vertex, then we will get a bunch of positive numbers. Starting from here, we will have like 3. We have 3 triangles instanced to this vertex. So we put a 3 here. And similarly, we have 1 here, 2, 3, 2, 2, 2, 1, and 5. And then we come back to 3. So in other words, by taking triangulation and record the number of triangles that are instanced with each vertex, we get a periodic sequence consists of positive numbers. And if we compare this sequence with the quantity sequence of the Frieze pattern we have seen before, we may notice that they exactly coincide. So we have 3, 1, 2, 3. It's like here 3, 1, 2, 3, and so on. And indeed, there's a bijection between the triangulations of polygons and such Frieze patterns, as discovered by Conway and Coxeter in 1973. In more precise terms, an n+3 periodic sequence is the quantity sequence of height n Frieze pattern, if and only if it arises from a triangulation of an n+3 gon. And this correspondence gives the bijection between triangulations of polygons and Frieze patterns. Yeah. But after these Frieze patterns were studied by Conway and Coxeter, it didn't get really, it was not the mainstream math until the introduction of cluster algebras and cluster categories by Fromming and Zelinsky in the beginning of 2000. So before moving there, we introduced another way to determine a Frieze pattern. So we pick up one integer from each row such that the entries in each pair of adjacent rows form a diamond. So we can see that these two ones, they stay in the same diamond, and these two ones as well. And such a configuration, we call it a lightning bolt, which here I denote those integers by orange color. And a priori, they don't need to be only ones. They can be other integers. But by choosing such a lightning bolt and applying diamond rules, you will get a Frieze pattern again. So, and what is the relation between the lightning bolt? I mean, say that how do we model this lightning bolt with some nice object that has some connection with the cluster algebras? And moreover, if we stare at this Frieze pattern for long enough, we would notice it's a symmetry called glide symmetry, in a sense that if you look at the triangle, which is colored in red, and the first column, we have 1, 1, 1, 2, 3, 4, 5, 1. And they appear again in this column, but in a reverse direction. 1, 1, 1, 2, 3, 4, 5, 1. And this pattern repeats. In other words, that this triangle, in some sense, is the fundamental domain of this Frieze pattern. And to get the other part of this Frieze pattern, we can flip this triangle upside down and translate it to the left and to the right. Then we will recover this Frieze pattern, the whole pattern. And this is called a glide symmetry. And to explain these phenomena, we need the knowledge of cluster category, which I will introduce later. Okay, before moving forward, let me introduce a simpler Frieze pattern. Well, here we fixed a row of ones on the top and on the bottom. And we choose a lightning bolt here. But here I didn't put integers. Rather, I put two variables, which is x1 and x2. And then I apply the diamond rule. For example, in this diamond, we have 1, x1, x2. And then we can calculate that this position, it should be a new variable, which is given by 1 plus x2 divided by x1. And similarly, if you look at this diamond, we have this entry and x2 and 1, and we can calculate this entry as well. And you can see that after several steps, this x1, x2 appear again. So one fact is that all the other entries are Laurent polynomials of x1, x2, the two variables we start with. And another thing is that if we specialize x1, x2 to be 1, then all the other entries will be positive integers. That means we get a Frieze pattern. Yes, and these phenomena, this Laurent phenomenon, and also this periodicity, like this glide symmetry, will be explained in the language of cluster algebra and the cluster categories. So let me, before introducing cluster algebras, let me introduce the definition of a quiver. So a quiver consists of the following data. So we have Q0, which is a set of vertex. It's called a vertex set. And I will label those vertex by integers 1, 2, 3 until n. And another set, Q of 1, consists of arrows alpha that goes from I to j, where ij are vertices, and it's called the arrow set. Moreover, we have two functions s and t, which specify the source and the target of each arrow. So for example, here we have this quiver with the 4 vertices and arrows between them. And there can be double arrows, like there can be more than 1 arrows between vertices, as we can see from this example. Today, we are mainly interested in those quivers which are called cluster quiver, in the sense that we do not allow loops and 2 cycles. So a loop is an arrow that goes out from a vertex I and come back to itself immediately. So this is not allowed. And the 2 cycle is given by is a pair of arrow between 2 vertices I and j, and the 2 arrows goes from I to j and j to I. So in the quivers we talk about today, we do not allow these 2 configurations. Okay, now let me introduce a mutation of quiver. So if we have a cluster quiver and we pick up a vertex k, then the mutation of the quiver at k is another quiver, which is obtained from q via the following procedures. So whenever we have a length 2 pass that pass through k, which means we have an arrow from I to k and an arrow from k to j, then we add an arrow from I to j. This is the first step. And the second step is that we reverse all the directions of the arrows which are incident with the vertex k. And finally, we would like to remove all the 2 cycles. So let's look at an example. We start from the following quiver, and we would like to mutate at vertex 1. So according to step 1, whenever we have a pass of length 2 that passes through k, we need to add an arrow. So here we can see that there's such a pass from 4 that goes from 4 to 1 to 2. Then we need to add an arrow from 4 to 2. And similarly, we have such a pass goes from 4 to 1 and 3. And again, we need to add an arrow from 4 to 3. So then we get the second quiver after the first step. And then the second step tells us to reverse all the directions of arrows that indices to 1. So there are 3 arrows that incidence with 1, 2 going out and 1 coming in. So we need to reverse the directions of all of them. Then we get the third quiver. And the last step tells us to remove all the 2 cycles. And there are 2 cycles. One is between 2 and 4, and another one is between 4 and 3. So we remove both of them. And eventually we get this type D4 quiver on the right-hand side. So you can check by yourself if you start from this quiver and mutate at vertex 1 again, you will go back to the original quiver that we start from. In other words, that quiver mutation is an involution operation. Yes. Okay. And now let me introduce the definition of cluster algebra arising from a quiver. It's a rather long definition. So we have a cluster quiver with the vertexes labeled by 1, 2, and 2n. And we pick up variables x1, x2 to xn. And we take the field of rational functions of it, which is this guy. And a cluster seed is given by a pair, which consists a quiver and a collection of rational functions f1 to fn, which comes from this field. And moreover, they form a free generating set, meaning that they're algebraically independent. And also, the smallest subfield that is generated by F1 to Fn is the whole thing. And we give them a name. They're called cluster variables. And so then we can very well get a bunch of cluster Cs, and they are connected by seed mutations in the following way. So we pick up a vertex from the quiver, and we can mutate the cluster seed with respect to this vertex. And the quiver will be just the quiver mutation at vertex K. And the cluster variables, the collection of cluster variables Fi will be modified in the following way. So all the others are the same, and only Fk is changed by this rule. And so this is a fraction, which in the nominator is the summation of two products. And these products is given by all the Fj's such that there's an arrow from K to J. And the other products is given by all the FLs where there's an arrow that from L to K. So you collect all the Fi's in which that there's an incoming arrow to your K, or there's outgoing arrow from your K. And you take these two monomials and take the summation and divide by Fk. And this is your new Fk prime. And so we start from the initial seed, which is Q and x1 to xn. And then we do the seed mutations. And the cluster algebra A of Q associated to the quiver will be the Q subalgebra of this rational field generated by all the cluster variables. Yes, this is a bit abstract, but let's look at an example. So if we have a quiver Q, which consists of two vertices, 1 and 2, and one arrow between them. And our initial seed will be this one, that we have this quiver, 1 to 2, and the cluster seed consisting x1 and x2. If we mutate at vertex 2, after applying quiver mutation, this arrow will be reversed. And we need to modify x2 as well, according to the rule introduced here. So we can see that in this quiver, there's one incoming arrow that comes from 1. So it takes the product of x1. And there's no outgoing arrow. So the other product would be just 1. And so we have 1 sum with x1 and divide by x2. This is our new variable. So this is mutation at 2. And as we mentioned before, that quiver, like this mutation of C's is also in evolution. So if we mutate at 2 again, we'll go back to the original seed. So we mutate at 1. Then the quiver, the consequence to the quiver is also the direction of the arrow gets reversed. And then we need to modify x1 in a similar way. It's the mutation rule. Then we'll get this one. And on the other hand, starting from the initial seed, we can firstly start mutating at 1. Then we get this one. And mutating at 2, we get this one. And 1 again. And this one. And if we compare these two C's, they're almost the same. It's just the position of 1 and 2 are swapped. So, and we take this as the same seed. So in other words, if you have a quiver Q, like this quiver, you have finite many cluster Cs. There are only 5. And you will have 1, 2, 3, 4, 5, 6, 7, probably 7. Oh, sorry, 5. 5 cluster. Some of the variables are the same. So you have 5 cluster variables. And the cluster algebra will be generated by these 5 cluster variables. And if you compare this thing with the Frieze pattern we have seen before, is that we start from x1, x2. By applying the diamond rule, we can substitute x1 by the new variable here. And then we get another pair, which consists x2 and this new variable. And we make use of these diamond, and we can substitute x2 by another one here. And then we get, again, another pair. Yeah, and eventually we'll go back to x1 and x2. So this feature is captured by in this particular example, this feature is captured by the cluster algebra of A2 in this case. And previously we mentioned that if we start from this x1, x2, this lightning bolt, and all the other entries can be expressed as Laurent polynomial of these two guys. And this is not a coincidence, and it was proved by Foming and Zalivensky in the setting of cluster algebras, that if we have a cluster quiver, then every cluster variable is the Laurent polynomial in the initial seed, x1 to x1, that we start with. And moreover, there's a bijection between the lightning bolt, or between a Frieze pattern and the cluster algebras of type A. So if we choose a lightning bolt in a Frieze pattern of height n, then every entry is obtained by taking a cluster variable of A of Q, where Q is a quiver, such that the underlying graph is just this AN graph. And if we specialize the indeterminant x1 to xn to the values of the Frieze pattern of your lightning bolt, then we'll get the whole. I mean, the cluster variables will recover the whole Frieze pattern. Yes, so now we have another bijection. And which explains the relation between the lightning bolt and the whole Frieze pattern. In a way that if you choose a lightning bolt, you will have an AN type diagram. Then you can freely choose the orientation. And this quiver, together with these variables from x1 to xn, will be your initial Cs. And then you apply seed mutation to them, and you get a bunch of other cluster variables, and they will give you the other entries of the Frieze pattern. And one last phenomenon we want to explain is this glide symmetry. So not only we want to know in this picture, not only we want to know that starting from a lightning bolt, how to get other entries, but we also want to get an overall understanding of this fundamental domain that consists of all the cluster variables, or the fundamental domain of the Frieze pattern. And to do this, we need the language of cluster categories, Well, the cluster category is constructed as an orbit category of the bounded derived category of something of the quiver. So firstly, let me introduce the what is called a representation of a quiver. So if we have a quiver Q, a representation of Q is an assignment of vector spaces to each vertex and linear maps on each arrow. In other words, if you think about this graph, you give some orientation of this graph, then you get a quiver. And then a representation, meaning that we put vector space on each vertex. And on each arrow, we put a linear map between the adjacent vector spaces. Okay, if we have two representations, V and W, of the same quiver, and the morphism of V and W consists of a collection of linear maps, phi I, which goes from Vi to Wi for each vertex. And moreover, these satisfy an extra condition that such a diagram should commute. So if we look at the first row of this diagram, that if we have we have an arrow alpha that goes from the source of it and to the target of it, and we put a representation V is the assignment of V and S of alpha and V T of alpha here with a morphism F of alpha. And another representation W is another assignment of vector spaces and linear maps. And the morphism between them are the collection of such linear maps corresponding to each vertex, such that this diagram commutes. And moreover, phi is an isomorphism if every phi I is an isomorphism of vector spaces. So we can consider the category of representations of the quiver Q with objects being representations and morphisms being these morphisms between representations. And then we get a category. And that's the main thing we start with our construction. So let's look at an example again. We take our A2 quiver as before. Then a representation of Q is given by two vector spaces, V1 and V2, and a linear map between them that goes from V1 to V2. So all such configuration would give us all the representations of a quiver Q. To get an overall understanding, like to understand the structure of this category, we would like to find the indecomposable ones, which in some sense are the building blocks of this category. So in this particular case, we consider the following three representations. So the first one is S1, in which we just put a one-dimensional vector space on vertex 1 and 0 on the other. And another representation X2, in which we put a one-dimensional vector space on vertex 2 and 0, the other one. And P1, in which we put one-dimensional vector spaces on each of them and identity map on the arrow. So it turns out that these three representations are the building blocks of the whole category. And of course, then there are morphisms between them. And moreover, we can visualize this category by another quiver shown as follows. So we have three representations, S2, P1, and S1. And there are morphisms from X2 to P1 and morphisms from P1 to S1. And in particular, there's no morphism from X2 to X1. I mean, the composition will be 0, and there's no morphism from S1 to S2. I mean, or 0 morphisms between them. And moreover, there's a functor, a translation functor, which I denote by tau, that will bring our object S1 to S2. And this is called the Ausland-Ruyten translation, and the whole quiver is called the Ausland-Ruyten quiver of Q. Yeah, and Auslander-Ruyten theory or higher Auslander-Ruyten theory are the big research area in representation theory, which I'm working on myself. Anyways, so now it's given a quiver, we introduce the representations, and we sometimes can visualize the category of all the representations by another quiver, which is called the Ausland-Ruyten quiver. And there's a translation functor which goes horizontally, and it to be important for us. This is enough. But to construct the cluster category associated to the quiver, we need the notion of the bounded derived category of the quiver. So it's another category, and the objects are given by such formal symbols, v shifted by I, where I is an integer and v is a representation of the quiver. And such symbols and also their direct sums will be the objects in the bounded derived category. And the morphism spaces are given by the following, which is kind of, if you know about it, it's the extension group between two representations, V and W, of certain degree. And the composition law of morphisms is given by the cup product of extensions. Yes, if your quiver is rather nice, meaning that if it is a tree and there's no relations, then there's only extension group in degree 0 and 1. But on the same time, these shift by 1 functor will be an autoequivalence of this category, so we can talk about the negative shift somehow. It's rather abstract again, so let's go back to our example. So we take the same quiver, 1 goes to 2. And so then the bounded derived category of this quiver can be visualized by the following quiver. So remember, we have seen here that the building blocks of this category of representations consist of 3 objects. So we have 3 indecomposable representations, and we introduce a shift to each of them for each integer. And for each integer, and so that explains like why these objects are given in this form. Of course, they goes to infinity on the left and on the right as well. And you may notice 2 things is that, so firstly, we have a translation functor tau that goes to 1 step to the left horizontally. And another thing is that there's almost a glide symmetry in this quiver, in a sense that if you stare at this small triangle given by S2, P1, S1, and if you flip them upside down and shift everybody by 1 and move to the right, and you get this triangle. And similarly, if you flip this triangle and shift every object by -1 and translate it to the left, and you get this triangle. So remember that we want to explain the glide symmetry of the Frieze patterns. So, but in the Frieze pattern, let me recall this picture. So we have this triangle situation, which is roughly like the fundamental domain of the Frieze pattern. And we flip this triangle upside down and translate it to the right or to the left, and it will be coincide with the corresponding part of the Frieze pattern. But here in our category, we have this triangle. We can flip it upside down and translate it to the right and to the left. But they are not exactly coincide immediately. There's a shift difference. So to manage that, we would like to somehow identify certain objects such that we get this glide symmetry. And to do that, and this is basically the idea of cluster category. So the cluster category CQ of a quiver Q is obtained by taking a quotient of the bounded derived category of the quiver Q by the composition of two functors, which is the translation functor and the -1 shift. So how does it work? Really? We still look at this quiver Q from 1 to 2, and we have seen the bounded derived category of the quiver Q. And by taking quotient, some of the object in this category would be identified. For example, if we look at S2 shifted by 1, applying the translation functor tau, we will get P1. And applying -1, we'll get P1 -1. And after taking the orbit, the object x2 shifted by 1 will be identified by P1 shifted by -1. And similarly, if you look at the object P1 shifted by 1, applying tau, you get S1. Applying -1 shift, you get S1 -1. And that means your P1 shifted by 1 is identified by S1 -1 in the orbit category. So, so roughly speaking, the cluster category CQ looks like this. So we identify, this object S21. This object is identified with this one. And this object is identified with this one. And this pattern repeats. And these 5 objects, which are in red color, are the kind of the fundamental domain of this category CQ. And if you look at this fundamental domain and you flip it upside down and shift it to the left, they will coincide with this part. Or shift it to the right, and they will coincide with that pattern again. So in other words, that this cluster category is the ideal place to capture the glide symmetry for the Frieze pattern. And moreover, remember that in the fundamental domain, well, these 5 objects, in this case, these 5 objects will be our fundamental domain. And remember that we have a cluster C's from before. And then we can do mutations to get all the other ones. Or like if you use the language of lightning bolt, we have the lightning bolt here, consists of x1 and x2. And by mutation, we get all the other entries. And then in the category here, there will be like special objects which plays a similar role as the lightning bolt. And by sort of mutation of this object, we will get other objects. So this fundamental domain consisting of these 5 objects are determined by even smaller, like even fewer objects, which in this case consists only 2 of them. And those special objects are called cluster tilting. So we need another notion which is called compatible if we have two objects in the cluster category CQ, XY. They are called compatible if the home space between from X to Y shifted by 1 is 0. And an object X is called rigid if it is compatible with itself. So those rigid objects are the special objects we are interested in. And moreover, we call an object cluster tilting. This object is given by n indecomposable direct summons. And it is called cluster tilting if every pair of objects, Ti and Tj, are compatible with each other. And of course, in this case, I can be the same as j, which means that each indecomposable direct summoned Ti should be compatible with itself. And so you can imagine that okay, maybe let's look at the example first. It goes more and more complicated. So we take the same quiver Q from 1 to 2. And in this case, there are only 5 cluster tilting objects in the cluster category. If we go back to this picture, one of the cluster tilting objects is given by the direct sum of these two objects, S2 and P1. And another one is given by the direct sum of P1 and S1. And similarly, we have the direct sum of S1 with X2 shifted by 1, and this one as well, and this one as well. So these are the 5 cluster tilting objects in the cluster category. So each cluster tilting object in this particular case is given by sort of like one arrow here. And if you compare with the pattern here, they coincide with the collection of cluster seed here. Okay. So there's a theorem which states as follows, that a choice of cluster tilting objects T in the cluster category CQ induces a bijection between indecomposable rigid objects of CQ and the cluster variables of A of Q. And under this bijection, cluster tilting objects will be mapped to cluster Cs. So here we start from a quiver Q, and with the initial seed x1 to xn, then we can define a cluster algebra. And there's cluster Cs and seed mutations in this picture. And with the same quiver, we can take its bounded derived category, and by taking an orbit, we get so-called cluster category associated to it. And in that category, we have some special objects, which are called cluster tilting object. And those objects will correspond to the cluster Cs. In other words, that this cluster category gives a categorification of the algebra of the cluster algebra AFQ. And with this bijection, I forgot. With this bijection, we could get another bijection between the lightning bolt of a Frieze pattern and the cluster tilting object of the cluster category. And that category models the glide symmetry of the Frieze pattern. And I think that's all I want to say for today. Thank you.
Thank you very much, Wei. Yeah, quite an interesting talk. Well, a lot,
Exactly. A lot.
a lot of it quite new for me.
Uh-huh.
Learn
I
much.
see.
Yeah, thank you very much. And now I will hit stop recording, and then we can have questions from the audience.
Sure.